In Chapter 24, we're going to look at data analysis and probability theory. This chapter is going to actually run across two different modules, and in the first module we'll look at sections 24.1, point 2, point 3, and point 4, and then we'll continue with Chapter 4 in the next module. Here, I'd like to introduce some basic concepts. First, a population consists of all possible observations from a distribution. A sample consists of a subset of a distribution. For example, if I wanted to talk about the undergraduate students of the University of Mississippi as a population, then I would mean all of the undergraduate students at the University of Mississippi. If I wanted to know the opinions of the undergraduate students at the University of Mississippi, I might very well collect a sample and just sample a few of them. I might, for example, stand at the flagpole on the circle at noon one day and ask the first 15 people their opinion on some matter and try to use that as representative of the entire population. So I'd have a sample of 15 trying to represent the views of the population of all undergraduate students of Mississippi. I'll come back to this example in a moment. A random sample involves elements chosen randomly from the population with the intention that the resulting sample will be representative of the population as a whole. In my sample of contacting 15 people at noon at the flagpole on the circle is intended to be representative of the entire undergraduate student body at the University of Mississippi. Do you think that's a valid sampling technique? Think about that for a minute. How might my sampling technique have been introducing bias? First of all, there are undergraduate students of the University of Mississippi that are at the Tupelo campus, so they would never be, or very unlikely that they would be at noon, so it couldn't be representative of them. Online students might not be there. Many students might not be out walking about at noon on the circle. You might have an entire class that just got let out, and the sample might be predominantly biased towards that class. So again, there are many ways that my sampling technique that I just dreamed up would not be representative of the population as a whole. So one must be careful when choosing a sample. If all members of a population are surveyed, it would become a census rather than a sampling, or rather than a sample. In 24.1, we look at data representation, and we'll introduce concepts on average and spread. The type of graphical depiction will depend on the data, on the distribution involved, the goal of your communication, and your audience. This is not an invitation to misrepresent data. Yes, many have said that you can lie with statistics. I'm certainly not trying to teach that, but I will show you how you need to be mindful of how you make choices in representing your data that can influence how your audience is going to take your data in. We're also going to look at different types of charts and look at some of the advantages and disadvantages of several. And I should mention that Excel isn't the best tool for some of these plots, and I'll show you an example of what I mean by that. Here's an example of a pie chart example, and it shows how you might allocate your investments in different types of investment vehicles, and it might help someone understand the relative portion associated with different parts of the whole. I grew up in a large family, so this is a very familiar task to me, the idea of slicing up a pie into 11 pieces and making sure that each piece was equally sized. A pie chart would be very useful for helping to detect slight variations in portion size. A bar chart would be an equivalent way of depicting it that may or may not give exactly the same information, but it does give the speaker a chance to discuss each one of the vehicles one after another, with its relative portion being more evident. Whereas in the pie chart on a circle, then you may not be able to control your audience, where your audience starts and where they finish when looking at the different portions. So the bar chart provides another way of showing them data. A histogram is probably one of the most common ways to depict a sample result, where you're looking at binning up your data into certain bin sizes and then expressing the relative frequency or the number of occurrences within each bin. And this is a set of soil sample results that came from a geological engineering senior design project, and we were looking at arsenic concentrations in nearby soils or near campus, and we found that most of the arsenic samples were following a fairly typical distribution where the relative concentrations were commonly quite low, but there were a few samples that had relatively high arsenic, and this was one way that we might depict that. But the bin sizes is one of the things that the user selects. Bins that are too large will not show sufficient distribution. Bins too small might show too many gaps or a spiky histogram. So here's different ways you might bin up that data, and you saw that distribution I showed in the previous histogram. Let's see how we could show this in another histogram. If I use very large bin sizes, it might cause you not to be able to see particular details in the distribution. Here's lead soil concentration, soil concentrations with a very large bin size, and if I used a smaller bin size, you'll see that there's actually something of a bump near the higher lead concentration levels that might be masked if I used a larger bin size. So here are some of the choices that the user will make will influence how the data is going to be perceived. This is an example of a different type of software package being used to create a histogram, and I actually prefer this one, but there are many different packages out there, and Excel is very difficult to get Excel to do exactly what you want, but statistical packages are available that are Excel add-ons or alternatives, and I don't want to discuss any of those because you'd need to be an expert at that, and we barely get into it in a course when I spend an entire semester looking at probability and statistics. So just know that there are better packages than Excel for creating some of the histograms or other charts that you might need for statistical presentation of your data. Beyond the depictions in a chart, there are certain kinds of metrics that we're going to get and observations that one could make about the distribution that you get. So now I'm going to start with qualitative descriptions of distributions. Based on a histogram, you might want to try and convey some information about it. You might look at whether the nature of the variation, for example. Is it approximately normal or bell-shaped, or is it fairly uniform across a set range of values? What's the nature of the distribution? Is it relatively symmetric, or is there skewness? A positively skewed set of data might look like the lead concentration data or the arsenic concentration data, where there's a tail pointing to the right, whereas a negatively skewed distribution might have a tail pointing to the left. You might also discuss the number of modes. How many bumps in your histogram? Is it really just unimodal? A bell-shaped curve would be unimodal. Or are there two bells in your distribution so it's actually bimodal? You might also ask, are there, and want to report, are there outliers present in the data that you need to discuss? Other sample statistics that you would likely want to report might include the sample mean, which is calculated using the equation shown, where you'd be summing up each of the terms and dividing by n the number of observations, or the range, which would be the largest minus the smallest. You might also report the sample median. That would be the midpoint in your data. To discuss median, you're going to have to take all your observations and order them from largest to smallest. Then if you have an odd number of observations, you would report the middle of those ordered values. And if you have an even number of observations, you would use the average of the two middle values. In very large samples, there might be no these might all come from the same particular value, so there would be very little difference. You might also present the sample mode, which would be the value with the most observations. More sample statistics include the sample variance, and that would be calculated here as s squared. And you might also I should mention that the sample standard deviation would be the positive square root of this, or s, is how we would present it. Notice that the denominator here includes n minus 1. The numerator includes each one of the observations minus the sample mean. Then you take that quantity and square it and sum all those values. So it can take you a while to calculate the sample variance by hand, and you might want to know how your calculator calculates variance. Almost all use the n-1 in the denominator, but a few, some Casios that I've seen over the years, use n in the denominator instead of n-1. So watch out and make sure you know what your calculator is doing. Another set of statistics would be to talk about percentiles or quantiles or quartiles. Some of the most common are the upper quartile, the lower quartile, and the interquartile range. The upper quartile would be the point where 25% of your sample is above and 75% below. The lower quartile would be the point where 25% of your sample is below and 75% above. And the difference between those would be the interquartile range. If you were collecting concentrations, you'd may have to be sure to report all of these statistics here. Well, the quartiles and the IQR, have to be sure to report those units. The units on the variance would be the square of whatever the units are for each one of your individual observations. By the way, when calculating the upper and lower quartiles and interquartile range, I recommend that you calculate the upper quartile as the median of the upper half of your data, and the lower quartile as the median of the lower half of your observations. Box plots are introduced in your textbook, and I'll spend a moment on them to describe them because you may not have seen them before. In order to calculate a box plot, you need to calculate the sample median, the upper quartile, and the lower quartile. You pick an appropriate scale that would allow you to express the full range of observations from smallest to largest. Then you create a rectangular box from the lower quartile to the upper quartile. You add a vertical line to the box at the median. Then you add a horizontal line in the opposite direction, showing the full range of values from the largest to the smallest. There are a number of different kinds of variations on the box plot. There's no single standard or accepted way to do it. Some might include the sample median and mean. Sometimes they show the outliers, and sometimes they have something called whisker caps. I'll show you with some examples. Here's an example of a box plot showing the lead concentrations from the same example I showed earlier when describing this sample with a histogram. Here you see this particular box plot has the whisker caps at the 90th percentage, and the lower one at the 10 when 10% of the data is below that point. Shows the outliers as single observations with the dot, and it also shows the black line, the black vertical line there in the center of the box plot is the median, and then the red line is the mean. How do I know the difference? Because notice that the box plot is outlined with black and the median is the more conventional one, so that's the vertical black line, and the mean is the vertical red line. There's one example of box plot. Here's some box plots that come from my research where I wanted to depict a large amount of data very succinctly, and I wanted to use these box plots to make the point that the chloride concentrations from producing waters from the upper Cretaceous units in Mississippi hydrocarbon production wells have a lower chloride concentration than the formation waters from either the upper Jurassic formations or from wells producing from the lower Cretaceous formation. And I got a whole lot of information expressed concisely with the single plot set of box plots. So there's an example, and that's it for 24.1.